This problem is on page 26 of your packet. It's the acid-base equilibrium AP practice problem, and it's just very similar to what an AP free response problem might look like. So we have the overall dissociation of oxalic acid. So we have H2C2O4. The key thing here is that it is a polyprotic or diprotic acid because of the H2. And this is unique because they're showing both hydrogens coming off at once. And I think there's actually a typo on this problem. What is that? There's the H2 written right here, but there should be nothing right there. That should be blank. Okay, so you can just cross out the H2. This is unique because they're showing both hydrogens coming off in one step, which doesn't actually happen. You have to remember that the hydrogens come off stepwise. They come off one at a time. So the K value that they're giving, the 3.78 times 10 to the negative 6, is actually a combination of the K values for both steps, Ka1 and Ka2. So we're actually going to see in a minute how that works. So we're going to erase that for now. Actually, let's just do that. Okay, and we're going to start looking at the parts of the problem. So starting with A, it wants to know what volume of 0.4 molar NaOH would be required to neutralize some mole sample of the oxalic acid. This is actually not anything to do with equilibrium. This is just stoichiometry. We're talking about combining NaOH and the H2C2O4 and just a regular acid-base neutralization goes to completion, so we do a single arrow. And what we know is the number of moles of oxalic acid, so that's 0.005 mole. And the question is what volume or how many liters of that. So this is just stoichiometry. So what we need is a balanced equation for this neutralization. So the sodium and oxalate are going to combine. This is like double replacement, so it's going to be Na2C2O4, C2O4, and H2O. And of course it has to be balanced. We have 2 hydrogens on the acid, so we need 2 right there and a 2 right there. The main idea here is that it takes 2 sodium hydroxides to neutralize 1 oxalic, and that's because the oxalic is diprotic. Again, the fact that we have 2 hydrogens there means that we need 2 sodium hydroxides to neutralize it. So we're just going to do our stoichiometry. So 0.005 moles of the H2C2O4 over 1. We bring that down, moles of, I'm going to say ox acid. That's easier. And then we're going to go to moles of NaOH. And we have mole to mole right here, so we just use the mole ratio, 2 moles to 1 acid. And then finally, we want to go from moles of NaOH to liters of NaOH. And the way that we go from moles to liters is using the molarity. The molarity of NaOH is given in the problem as 0.4, so that's 0.4 moles for every 1 liter. So this is our setup for part A and solving how many liters of NaOH would be needed for neutralization. And so the answer that we get is 0.025 liters of NaOH. Again, this is not necessarily specific to this equilibrium chapter. This is like, honestly, this is like pre-AP chemistry. Okay. The next part is not pre-AP chemistry. Part B is actually getting into the equilibrium stuff. It says to first give the equations representing the first and second dissociations of oxalic acid. So what this part B is wanting us to do is to take this equation from part that was given, this equation here, and separate it into the 2 individual steps and show the hydrogens coming off at once. So we have H2C2O4. We're going to show the first hydrogen coming off, and the leftovers are HC2O4. Whenever a hydrogen comes off, the charge just goes down by 1, so it becomes negative. So this would actually be called Ka1, whatever the K value was, we don't know it. Our second dissociation shows the product of the first one losing its hydrogen. So C2O4 minus, double arrow, the hydrogen comes off. The oxalate ion is left by itself, and so we have the typical -2 charge of oxalate, and this would be Ka2. But again, we do not know it yet. Okay. The second part of Part B says calculate the value of the first dissociation constant K1 or Ka1. We're looking for this value right here, Ka1. If the second value is 6.4 times 10 to the -5th. So this is 6.4 times 10 to the -5th. Okay, so we know Ka2. We're looking for Ka1. What is the relationship between these two? That's the key thing that we need to remember. So over here on a clean slate, let me remind you that if you add equations, you multiply the K values. Okay, so adding equations is like the multiple steps of the acid dissociation. If you know the overall K, that's for the added equations, you can find the individual K values. So, in other words, K of the overall equation equals Ka1 times Ka2. And if you remember back from the very first slide, this is the K overall, okay, because it's showing both steps at once. So, I'm going to remember that number, 3.78 times 10 to the -6. 3.78 times 10 to the -6 equals Ka1 is what we're looking for, multiplied by Ka2, which is given right here, 6.4 times 10 to the -5th. And so to solve it, we just divide. That will cancel out. We put 6.4 times 10 to the -5th. So we divide the overall by Ka2, and that's going to give us Ka1 for our answer. So Ka1 is those two numbers divided. We get 0.0591. And that's actually, that's not very small for a K value. If you think about the decimal, it's just times 10 to the -2. So that's not a really, really, really weak acid. It's borderline strong-ish, we could say. Okay, so we know the Ka1 and the Ka2 now. Let's move on to Part C. It says to a 0.015 molar solution of oxalic acid, so 0.015 molar H2C2O4. That's what we have. A strong acid is added until the pH is 0.5. So strong acid makes the pH 0.5. Okay, we want to calculate the oxalate ion concentration in the resulting solution. What we want to do here is remember that the strong acid, if you have a mixture of a strong acid and a weak acid, the strong acid is the only one that produces a significant amount of hydrogen. Okay, so we can find out the hydrogen ion concentration from the pH from the strong acid and assume that really not any of it came from the oxalic acid, so it's just all from here. So we do 10 to the -0.5. So the hydrogen ion concentration, if we put that in our calculators, is, let's see, 0.316 molar. Okay, so what we know is the hydrogen ion concentration. And again, the question is the concentration of the oxalate ion. Okay, if we think about this, we want a K expression that has both of these in there, the oxalate ion and the hydrogen ion. And so, and we also need to know an initial value of something. So what we're going to do is actually use the K overall expression and plug in what we know. So the K overall expression, remember, is hydrogen ion, but it is squared, okay? The oxalate, C2O4, which is what we're looking for. On bottom is the H2C2O4. So we need to plug in what we know here. The K overall is known. The hydrogen ion concentration is known. That's right here. The oxalate is what we're looking for, okay? And then the original oxalic acid is also known. The original oxalic acid is the 0.015, okay? So we're going to take all of those numbers. I'm going to go to a clean slide, and we're just going to plug those numbers in to solve for the oxalate amount left over. So again, K overall, we're doing hydrogen squared oxalate over the oxalic. So K overall was, let me see, I don't have this written down, 3.78 times 10 to the negative 6 equals, the hydrogen value was 0.316 squared. I'm going to call the oxalate X, and the oxalic was 0.015. So you just do your algebra to rearrange and solve. Feel free to pause it and try it on your own. We get that our X value, which is oxalate, is 5.7 times 10 to the negative 6 molar. Okay, our final part is D. We want to calculate the value of the equilibrium constant Kb for the reaction that occurs when sodium oxalate is dissolved in water. So sodium oxalate, when we're looking at this, the sodium is not going to affect the pH because it came from a strong base. The oxalate is going to affect because it came from a weak acid. So since oxalate came from a weak acid, it is a strong conjugate base. All right. To prove that, we can show that C2O4 minus 2 interacts with water in the way that a base does. Because it has a negative charge, it's able to take a hydrogen from water, and remember, it only takes one at a time. So HC2O4 minus, and when it takes the hydrogen from water, it leaves behind hydroxide. So what we have here is our equation to show how C2O4 acts like a base. If we want to get the Kb for this, we need to remember that the Kb for oxalate multiplied by the Ka for its conjugate, which is the hydrogen oxalate, multiplied together give you Kw. Now the question is, which Ka value do we use for right here? Because we have K overall, Ka1, and Ka2. Because this equilibrium is between the hydrogen oxalate and the oxalate, and that's the equilibrium, that's like the opposite equilibrium for Ka2. If I show you back here, this was Ka2, and these are the two chemicals that we're looking at in part D. The value that we're going to use is the Ka2 to substitute in right here, so that's going to be Ka2. All right, so Kb is what we're looking for. Ka2 was 6.4 times 10 to the negative 5th equals Kw. So it's simply dividing and solving. So feel free to pause it, solve it on your own. Remember that Kw is 1 times 10 to the negative 14. The answer that you get for Kb is 1.56 times 10 to the negative 10. So this is showing us how what looks like a neutral salt, sodium oxalate, actually can act like an acid or a base. The ion that came from a weak acid or base can affect your pH. So that is the end of this problem. Good job.